All right, so let me introduce the next speaker, which is Sebastian, and he will talk about the past, present, and future of the language server. So the talk after this one will also talk about the language server, so they are kind of shared or joint in a way, but we're sticking to the schedule and treating them as separate talks. So whenever you're ready, the floor is yours.
All right. Hey, everyone. Yeah, as Frederick just said, I'm talking about past, present, and future of the Julia language server. Let's start out with a brief history of Julia IDEs, Julia tooling. There are a few Julia-specific IDEs and editors in the past 12 years now, I think, since I've been kind of involved with the Julia community. And yeah, these are some of them. In the olden times, there was Julia Studio. It was a Qt-based, Julia-specific editor built by Forio, and it only worked for Julia 0.2. So when I kind of tried to use Julia 0.3 and tried to find an editor, I tried this. It didn't work, which was a bit unfortunate, but there luckily were some alternatives in the work. In 2014, Mike Innes started work on the light table-based Juno editor. Light tables, at the time, very visionary IDE, I guess, built on Clojure and a bunch of web tech, essentially. And it was meant for Lisps, but as you all know, Julia basically is a Lisp, so it seemed very appropriate to hook into that. And the vision of light table was to allow for very interactive development in the editor, and what Mike built with Juno sort of followed along those lines. But the initial implementation didn't have any particularly advanced editor features, no like IntelliSense or stuff like that that you might expect. Light table slowly died. But GitHub worked on the Atom editor, which also built on WebTech, but no Clojure, so maybe a bit easier to get into. And yeah, fun fact, Electron, which some of you might know as sort of the framework that a bunch of desktop applications are nowadays built on, like Slack or whatnot, was originally called Atom Shell and was written especially for the Atom editor, and then just kind of took off on its own. The Juno editor in Atom also focused mainly on full interactivity. It could display plots, had a debugger built in, had a workspace, inline evaluation, of course. That was sort of the main thing inherited from the light table implementation. And slowly but surely, some more static analysis-like features crept in, especially when Shuhei sort of joined the team and did a bit of work on that. Unfortunately, Atom also got sunset a couple of years ago, so Juno is no more. But development did move to VS Code. I'll get to that in a little bit, but first I'll just give a very brief overview of the architecture of the Juno IDE. And yeah, essentially, the client, Juno, Atom, would talk to the REPL process for everything it needed to either evaluate code or show plots, show the debugger, whatnot, but also to fetch information about the code base you're currently editing, so to get global completions, which would be implemented by reflection, right? You just ask Julia which names are available in a given module, but also local completions, and these are then built on a custom parser. And that's CSD parser. I'll talk about that at a later time as well. So this architecture is mostly fine, except when it isn't. If you're running the REPL and code analysis in the same process, in the same thread, then obviously the two will conflict at some point, and it turns out people don't like it very much when their DiffyQ solver runs an order of magnitude slower just because you open two files at the same time, or just stalls. So that was a big issue with loading the code you're trying to run and the code that's responsible for analyzing what's currently open in the editor into the same process. And yeah, crash is also a big thing, right? If your REPL process dies because of some code you've written, then you also don't get any in-editor completions, for example, which is a bit annoying. As a sort of second point, which isn't really related to this architectural choice, but any kind of analysis we had was fairly basic. There were some local completions and so on, but nothing particularly advanced. But that's something that could have been fixed if the hours had been put into that. All right, anyways, let's talk about the present, I guess. The VS Code editor itself, I'm not sure when exactly they started working on that, probably like 2015, 16-ish. But the Julia side of things started out in 2017, so it did live in parallel to Juno. David and Zach laid the groundwork for sort of both the extension for VS Code and also the Julia side of things, which is the whole language server ecosystem, essentially. And in 2020, when it was, essentially when Atom was sunset, the remaining Juno team sort of joined forces with David and Zach on working on the VS Code extension and the language server. All right, so to the more in-depth part of this talk. The way Julia and VS Code works is that there are three main parts. The client, which in this case is VS Code, but in theory could be any editor. The whole point of the language server approach is that it's fairly agnostic towards which client is talking to the server. A REPL process for all of the interactive needs, which sort of got inherited from the Juno approach, and then a language server process that itself had a bunch of dependencies layered on top of each other. All communication between these three processes was handled via JSON RPC. That seemed like the obvious choice. And the REPL process itself, as I said, handles all interactive features, so it does code evaluation, plotting, profiling, debugging, table rendering the workspace, and all of the other fancy interactive stuff. It also has some limited support for introspection. So for example, we can fetch information about which modules are loaded into the REPL process or get REPL-like completions based on the REPL state. However, that's not the main source of completions and other info about symbols in your editor. All of that is based on the language server process itself, which contains, as I said before, like a bunch of packages layered on top of each other, and I'll go into detail as to what these do in a bit. As sort of the overarching design goals of the language server implementation, there were probably more than three, but these are, in my opinion, the most important ones. First is that the language server process never runs any Julia, or not any Julia code, any user code to circumvent the issues we had in the Juno implementation, essentially. So nothing the user can do in their REPL process should be able to take down the language server process. Second one is crash fast, fix fast. Whenever something would go wrong in the language server, it would just crash up, print an error message, and if you've opted into that, send telemetry to the developers, which at the time allowed us to fix a bunch of issues very quickly because we saw them as soon as they happened, essentially. And the third one was that it needed to be fast. You want to get feedback on essentially every keystroke. You want to know if you've just type out the variable name you're typing, or completions need to take into account what you've just typed, otherwise they're going to be essentially useless. As a quick aside, the language server protocol is what ties together the client and the language server. And this was a standard pioneered by Microsoft to connect arbitrary editors or clients with servers, language servers, that would provide all of the fancy IntelliSense feedback that you'd expect in an integrated development environment. And it was basically developed in parallel to the main VS Code editor, so it's very, very much tied to that in a way, but at least in theory, it's supposed to be completely independent and can be adopted by various editors. And that has in fact happened, so NeoVim, Emacs, Atom, and many others that have implemented generic language clients or extensions for language clients that you can use to connect to basically any language server. And the way this protocol specification works is that it specifies which messages can be sent from the client to the server, how the server is supposed to respond to those, and it's completely JSON RPC based. All right, so let's take a look at how the Julia packages are implemented that power the language server. The sort of top level here is LanguageServer.jl, and this package essentially contains the interface specification, so it's essentially a mirror of the JSON spec that Microsoft designed for the LSP. So it implements Julia types for all of these. It sets up the client-server communication handlers for the various RPC methods the spec prescribes. It handles text document sync and workspace management, both of which can get complicated if you care about performance, especially if you're working with big files or if you're working on a remote server, because then you don't want to send the whole document across on every keystroke when it got updated. So in theory, the underlying infrastructure supported incremental sync before. Right now, I think that's essentially disabled for correctness reasons, but the spec at least supports that. Workspace management is also very much tied to Julia environment management. If you have a workspace open and that has a project.toml and a manifest.toml, then we can take that into account and figure out which dependencies you're loading, and this will get important further down the line. Yeah, and lastly, it also sets up the sort of request handler loop, right, that handles communication to the client and dispatches incoming messages to the correct handlers and prints the responses back to the communication channel. Communication is typically handled via pipes or sockets. Theoretically, there are also modes where a client can connect to the language server via standard in, standard out, but that seemed a bit more brittle than what we've gone with. Okay, so what features does LanguageServer.jl support? Some of what you'd expect, right? Completions, documentation about a method or a binding if you hover over it with your mouse or with a cursor. Auto-completions, some basic support for refactoring. So for example, you can rename a method or a global variable at its definition site, and that will then also make the according change at every reference to it. And speaking of, we also have support for the go-to definition or find references tasks, I guess. You can get signature help. So if you're typing a function, then you get a list of methods of that function and associated types. There's some support for test items. So if you're writing a Julia test file, then you can, in theory, run those piecewise. In practice, I think that's currently in a bit of a brittle state. We have some very basic support for inlay hints. So if you type if you're inside of a method or inside of a function call, then we can, for example, give you information about which keyword argument you're currently, or which positional argument you're currently sort of specifying, right? Because those don't show up in contrast to keyword arguments. And we also have built-in formatting via Julia Formatter. Also, there are some custom request types for VS Code specifically. These could get used by other clients as well, but aren't right now because these are mainly required by some of the more interactive features that the VS Code extension itself requires. And yeah, I've listed them here. Basically, things like, if I give you this cursor position in this document, then tell me what module this is in. And that's, for example, required for the inline evaluation feature because that allows you to evaluate certain code into a module. There's also like some basic block analysis also required for inline evaluation, and that will tell you which is like what's at this cursor position the biggest non-module block essentially. So that's sort of our heuristic for figuring out which piece of code makes sense to evaluate in this context. And then there's also a bunch of stuff for documentation and tests, but I won't go into that too much here. Right, so if you remember that big stack of packages in that diagram I showed, at the bottom of that there was Tokenized.jl. That's a library that I think Christopher wrote originally, and that breaks a text document or a string into a token stream, and that can then be ingested by a parser. It still exists standalone, but also is now part of JuliaSyntax.jl. And yeah, if you're looking at using it, that's the version you should use. It's a bit more up-to-date and bug-free than Tokenized.jl itself. But yeah, in this example, you can sort of see how it works, right? It breaks the foo.bar string into a bunch of tokens and assigns byte positions and sort of kinds, right, types. So foo and bar are identifiers, whereas the dot in between them is an op or operation. Yeah, and parentheses and all of that stuff is nicely handled. This token stream is then parsed into csdparser.jl, which, as the name implies, parses Julia code, but it does a little more than Julia's femtolist parser, which at the time was the only option. There was no JuliaSyntax.jl at that time, in that it gives provenance info for every syntax node that gets produced by the parser. And that's important because that way we can track error information, for example, back to your position in your document. Otherwise, every bit of like linting and whatnot would be super imprecise, and stuff like auto-completions, for example, would be basically impossible without some very weird heuristics. CSD parser produces a tree of expr objects, not the Julia expr, but all caps expr, and that can be converted to Julia expressions, as the last line in that code block shows. This all caps expr object looks somewhat similar to Julia exprs in that there's a head and a bunch of arcs, but it also carries a bit more data around with it. For example, like trivia, which is essentially white space, and also information about where in the document it occurs. An important point to make here is that the node kind is not encoded in Julia's type system, right? Expr is not parameterized on the kind of the kind of the node, and that has to be that way because of performance reasons. A syntax tree is notoriously sort of type unstable, right? You can't tell anything about which child node will occur in a given expression. So it would just blow up the type system essentially, and have a bunch of dynamic dispatch. This last field, meta, is used to put context into the syntax tree. This will be important in the next step. Whether or not it's a good choice to put all of this meta information directly into the syntax tree, I'm not so sure about. It's probably not the greatest choice. All right, let's talk a bit about static-lint.jl. Yeah, as the name says, it does static analysis of code. However, it does also a bit more than just linting, so the choice on name is maybe not the best. But the important piece to focus on here is the static part, right? All analysis happens without ever loading user code, right? And in a way, you can think about static lint as a re-implementation of lowering or parts of lowering. So it does binding resolution and scope handling and so on. But at the same time, it's a very basic re-implementation and certainly not a bug-free one. So that obviously opens its own can of worms. Yeah, staticlint.jl takes CC parser.expression as input and runs essentially two passes on it, right? Some initial marking of bindings and globals, some very limited macro handling for like very trivial cases like basenode at no specialize or also base.eval and so on. As I said, it handles scope analysis and reference resolution and sort of puts all of these into the syntax tree essentially. And then after it's run through a whole module, for example, it runs another delayed pass to re-resolve references that might have been defined in the meantime, because if you're recursing through the tree, you might run into bindings that actually get defined later on in the document. And lastly, it'll run some very limited type analysis as well. Yeah, this is sort of a very basic example here, right? 2 plus break doesn't make any sense. So if we lint the string, we get a error object put into the meta object of the first argument or the third argument of the first argument of the produced syntax tree, right? And this is okay. Yeah, a break should happen in a loop, right? Don't just write that outside of a loop. Writing rules, as we've heard, is not super straightforward. So this is a very simple case where it's just about checking if a non-data type is used in place of a type declaration. So this is a very localized example. However, everything that's a bit more complex or needs non-local data is pretty annoying to write. It does, however, have some support for figuring out where binding comes from. So, for example, it can distinguish, let's say, test.addTest from just some arbitrary addTest macro that got defined somewhere else. It is technically possible to run staticlint standalone, for example, in a GitHub action. But yeah, please don't. It's annoying to set up, and the output is pretty, yeah, it's not great. But it's technically possible. Yep. Okay, yeah, bunch of alternatives to sort of the staticlint stuff, right? Relint, as we've heard. There's also SumGrep and Argus, which are two projects pretty much in their infancy. And then on the not quite as static side, there's jet.jl, which we'll hear about in a bit. All right, so the last piece, I think, in the language server box I had in that diagram is simulserver.jl, and that does actually handle everything that's got to do with external dependencies of the code base you're currently editing, so everything that got pkg added to the environment. This is not static at all, right? It's completely reflection-based. It loads your packages that get sort of enumerated in the environment. It extracts binding and method information and then writes that back to disk. So that is subsequent run of LanguageServer.jl on that environment can just deserialize the cache and use that information. Yeah, this is sort of the steps that SimulServer runs through. So as I said, it loads your package with basically no compilation at all. So everything that we can disable gets disabled because that should hopefully speed up package loading by quite a bit. It fetches all names in all defined modules, so it just recurses through the module tree. It attaches documentation to bindings. It enumerates methods that get defined. It asks the Julia compiler for return type info. That's not always possible, right? But if you have a fully concretely typed method, then we can get some info on that. It figures out which bindings get exported or re-exported, and then in the end writes everything into a custom binary format because custom binary formats are great, right? Mainly for performance reasons. Deserialization needs to be fast. All right, let's really quickly talk about issues with the current language server implementation. First one is probably performance. Both static lint and symbol servers are not super robust and can run into edge cases where they just take up a lot of memory, and the Julia process might get killed or a computer might crash, stuff like that. It's not great. And also, if you run into very big documents, for example, MTK-generated files, right, a couple megabytes big, potentially very deeply nested syntax trees, then static lint basically ends up choking on those, might also run into stack overflows because of the way it's implemented and so on and so forth. A second sort of big issue is the power of this approach, right? It is fully static, so it can't really do any of the fancy stuff the Julia compiler does itself without invoking the Julia compiler, and to invoke the Julia compiler you need to load the code, which isn't static anymore. So yeah, we're out of luck in that regard. If we were to sort of relax at our working design goal of wanting the LS to be fully static, then it's possible to do a lot more, and that's something we'll hear about in a little bit. Macros are also a very big issue, right? We can special case some of them, very few, but everything that's actually, does something that is reflected in the resultant syntax tree we cannot look at, because that also needs the runtime, right? Macros can execute arbitrary Julia code. Speaking of crashes. Oh, nice. Yeah, I think Julia process was taking a lot of memory or something and got killed. Funny coincidence. Right, so other issues, maintainability and extensibility, right? We heard a little bit about that in the relent talk as well. Static lint itself is not super pleasant to work with. Writing new rules is hard. And generally, all of the CST parsers, static lint, symbol server, language server code base is a bit hard to get into. And also, it needs to be maintained in parallel to every implementation of the parser in Julia base. So whenever someone wants to add some fancy new syntax to Julia base, right, they make that change in JuliaSyntax.jl nowadays. But it also, someone also needs to make that corresponding change in CST-parser.jl, which is extra work. All right, so what's next with the current language server? It'll be maintained for some definition of maintained for the foreseeable future, but it's fairly unlikely to be actively developed too much. However, there might be something else in the future. So I'll refer you to the next talk. And yeah, if there are any questions, we can maybe take some now, but otherwise I'll be around after the next talk as well. Thank you.
So if there are any quick questions, we can take it now, but Sebastian will also reply to questions after the next talk. So yeah.
When you update the support for new syntax, what happens when somebody loads an older, like a file from an older version of Julia? Do you fall back to previous code version?
So the goal of CST parser is to support basically every Julia version since LTS. In practice, it probably supports a few more as well. And yeah, basically it switches based on the version the language server is running on. So there are a bunch of if conditions in there that look at the current Julia version. In theory, we could refactor that to look at sort of supplied Julia version, right? So that you can run a newer Julia version and load older code. But in theory, it should all work, yeah.
Quick question. Thank you very much for static lint, first of all. And what about syntax highlighting? Is it something that you are supporting, or because you haven't mentioned that? So
sorry, say again?
Syntax highlighting.
Yes, so that's not currently in the LanguageServer.jl implementation, but the LSP specified support for syntax highlighting. So yes, we could do that. And it probably wouldn't even be that much work, but also, yeah, performance sensitive. And I think the current Julia for example, regular expression-based grammars or the tree-sitter grammar for Julia aren't that bad. So basically, no one's really looked into it so far.
All right, so let's thank Sebastian once again. All right, so while